Alright, yet another throwback question. So this is an Atwood machine. It's one we've done before where we solve for acceleration of the system. And we could solve for acceleration and then use distance to figure out what the final velocity is, but here they're having us try to do it using conservation of energy. And so we should see that it's a little bit easier to do, at least it's fewer steps. But we need to figure out, well, first of all, let's call this block A over here on the left-hand side. And so block A, at the beginning, initially, block A has 0 kinetic energy. So I'm going to call this K for kinetic energy. The subscript is A, that's for block A, and then O is going to be for original. So the original kinetic energy of block A is 0, because it's not moving. Now, if I look at the gravitational potential energy of A, so this is UG for A, and that's the original. So it's a bunch of subscripts, but this is the original gravitational potential energy of block A. So each subscript has meaning. And that is not equal to 0. So it has some energy at the beginning. Okay, let's talk about the final states of block A. So I have the kinetic energy of block A that is final. That final energy is not going to be equal to 0. In other words, the system's going to start moving. And we understand that the final velocity of block A has to match up to the final velocity of block B because they're attached by a string. One can't move faster than the other. Okay, now we have UG for block A, but this will be the final potential energy. And so looking at that, we can see that block A is going to be all the way down at the bottom. In other words, it's going to trade places with block B. So it'll be at a lower level. And so the final energy, final gravitational potential of block A is going to be equal to 0. All right, let's do the same thing for block B. So block B is the block on the right-hand side. And so we'll have the same variables, just with the letter B instead. So the original kinetic energy of block B will be equal to 0, because it starts at rest. The gravitational potential energy of block B originally is at the lower level at the beginning, at the start, so that is also equal to 0. We have the final kinetic energy, KB final, and it's going to be moving now, so that's not equal to 0. And then we're going to have its final potential energy, so we have UG for B, but this is the final one. And B is going to be lifted up into the air, so at the end, B is going to end up with some potential energy. It's not going to be equal to 0. So we're doing this just to kind of keep track of what kind of energy do I have at the beginning, what kind of energy do I have at the end. So let's separate these into beginning. Anything above is original. That's what it starts off with. And I'm looking for the variables that are not equal to 0. Well, at the beginning there's only one variable that's not 0. So that means that all of our energy at the beginning is going to start off with the gravitational potential energy that's stored in block A. So UG A naught. That's what we begin with. That's equal to the final energies we end up. Well, at the end, it looks like we're ending up with 3 different types of energy. So I'm looking at the three that are not zero. So 1, 2, 3. Those three are going to be on the right side of my equation. So we have block A has some final kinetic energy, and block B has some final kinetic energy. And then block B is going to also have some final gravitational potential energy. Okay, so that is our equation, and that's how we derive our equation. We probably could have done this a little bit easier if we just done a LOL bar chart. In hindsight, I don't want to start the video all over again to do that. But we could have done it that way as well. Alright, so let me clear this up. And now that it's cleared up, let's go ahead and start expanding our equation. So it looks like a long equation is going to get worse. So the equation for potential energy, this is the mass of A times gravity and then times height. And we know all three of those variables, so we can plug them in momentarily. We're also going to have the kinetic energy of A. So on the right side, for the final situations, we'll have the kinetic energy of mass A, and that's times velocity squared, plus the kinetic energy of B. So this is going in here, this one goes up there. So this is for mass B, and that's its velocity squared. Both of those are final velocities. Plus, since mass B is getting hoisted up into the air, it's going to end up with some potential energy. So this is mass B times gravity times height. Alright, we know all of those variables. I know both masses, I know gravity, I know the heights are technically the same. So now we just need to start cleaning up the equation. So I'm just going to keep moving my equation up, and let's get similar variables on the same side. So that's my first order of business. Alright, so we're going to do mass of A times gravity times height, and we are going to subtract out the mass of B times gravity times height. That's going to be equal to essentially the kinetic energies, 1/2 mass of A times velocity squared plus 1/2 mass of B times velocity squared. Okay, let's simplify. So I can pull like terms out, and that'll make it just a little bit cleaner. So over here, I'm going to do parentheses, and I'm going to pull out the G and the H. So this is going to become the mass of A minus the mass of B. Oops. Times GH. And we'll do the same thing on the right side. We can pull out the fraction and we can pull out V squared. And so on the right side, that's going to become the sum of the masses, MA plus MB, and we're going to do V squared over 2. So the 1/2 is still there, we're just dividing the 2. Alright, that's giving me fewer variables, so it's looking much cleaner and more representable. We're solving for the velocity. So here we go for velocity. Let's go ahead and clean this up again. Let me go ahead and erase what we haven't used so far, or I guess what we don't need anymore. Okay, and we're going to go ahead and move our variables to the left-hand side. So to get rid of the v squared over 2, to get rid of the 2, we're going to go ahead and multiply it across both sides. So we'll multiply 2 in front of the left side, and we'll multiply by 2 on the right side. Of course, 2 over 2, that'll reduce out. It'll go away. And then all we have to do is just divide by the parentheses. So we divide all of this by MA plus MB. And I divide my left side by MA plus MB. That will go ahead and get rid of the parentheses on the right hand side, and now we have isolated v squared. So of course the final step to do is just to take the square root of that big huge mess we have. But we can sort of see a relationship that pops up. It should look a little bit similar to what we did for acceleration. So if you recall, acceleration was the difference in mass times gravity over the sum of the masses. This is, interestingly enough, it has similar elements. Okay, well, enough of that. Let's go ahead and throw some numbers into this. So v equals the square root two parentheses, MA is going to be 5.5 minus 3.7, and then that's times gravity, which is 9.8, and then times our height, which is 7.3. All of that is divided by the sum of the masses, which is 5.5 plus 3.7. Okay, so that's doing it all in one step, and that's going to give us a final answer of 5.291. And so that's going to be my final answer. Of course, if you don't want to do that big huge equation, by all means you can substitute in earlier and just clean up the math on your own.